Greetings and welcome to the first seminar in the 2023 Science in the News Public Seminar Series. This is a series that will have 5 talks this fall over the next few weeks on Wednesdays at 7 p.m., both live streamed to YouTube and also in Northwest Building's B103 on Harvard's campus. So the format of the talk tonight will have 3 parts, and each part will be about 15 to 20 minutes long. After each part, we will break for questions. Feel free to submit any questions that you have in the YouTube chat at any point during the talk, and we will relay them to our speaker. And then we will work our way through the talk. So tonight's speaker is Young-Chao Chen, a PhD candidate in electrical engineering here at Harvard, and he's going to be telling us about whether ChatGPT is the robot brain that we've been waiting for.
And so, hello everyone. My name is Young-Chao. I'm right now a third-year PhD student in Harvard C's electrical engineering, and I'm studying the robotics. So today my talk is about is ChatGPT the brand that robots have been waiting for. So when talking about robots, one question I would like to first start is, what is called a robot? So here is the definition from the Wikipedia, and we can see that from the definition, a robot is a machine, especially one programmable by computer and capable of carrying out a complex series of actions automatically. So you will find that this definition is quite complex and it's very broad. You don't know what a real robot is. But actually, from my perspective, I think everyone already has a man of what kind of robot he wants, because robots, the end goal is to give the service to the humans. So humans should be very familiar with what kind of robot they have. For example, these are the robots that these 2 images are generated from the text-to-image model. I mean, the recent very hot diffusion models. And then we can see that these 2 robots actually are what in our mind and what we want. In the first picture, this robot is a very common, is a very capable house robots that this robot is doing like cooking and all kinds of the room tasks. And then another robot here in the right side is a robot that's doing the office tasks to us. And so we can see that for these 2 robots, they have very general capabilities to do different kind of tasks. And but one question is that these 2 robots are very ideal in our mind, but in our real life, currently we don't have this kind of robots right now. So my question is, why these robots are still lacking in our daily life? Then, for my talk today, I would like to discuss about this problem. Like, first, in the part 1, I will discuss like challenges in the current robotics domain, and then what insights or what opportunities we can get from the current ChatGPT, very hot topic. And then another topic I would like to discuss is about how to connecting the ChatGPT with the real world. And then in the third part, I will discuss the future prospects in ChatGPT robotics. I will discuss some possible challenges and the solutions to the application of ChatGPT into robotics domain. So first, let us come to the first part. So as I mentioned about, robots still lack the presence in our everyday life. And for the real applications of robots in our current life, we will find that they are just limited in some specific domains or specific applications. For example, these 3 are just the 3 very common applications. The first is the cleaning robots, and another is the Amazon warehouse robots, and the third is the manufacturing robots. And we will find that these 3 robots, they are totally different from what we dreamed, and that's the general robots I have discussed before. So what are common characteristics they have? So I think a common characteristics they have is that these robots, they are specialized in one task but lack intelligence. So I mean, they are specialized in the cleaning, but they cannot handle the other tasks. They are specialized in the warehouse, the pick and place, but they are not targeted as other tasks. So that's the main difference from these robots to our ideal one. Then to get ideal robots like what we want a daily robots, and a daily robot that can help you in our common life. Then our question is, what kind of the requirements we need for these robots? And I mean, what's the bottlenecks we can face? So here in this image, it's a very common situation. I mean, in the center there is a mobile robot. I mean, this mobile robot, it can move around the room, and then it has a gripper so that it can do the pick and place, this kind of tasks. And then this robot, our humans will give it some instructions with language instruction, like I spilled my code, can you bring me something to clean it up? Then in this way, to our humans, if we do this task, it will be very simple because to handle this task, we just randomly find something to clean it up. Yeah, that's all. But actually, if we think carefully, there are we can divide this very hierarchical task into the subtask sequences. I mean, we can. The reasonable thinking steps is like, first, what tools can be used to clean the code, and then where is the tool, and then the third is how to bring it to the user. So we can divide this hierarchical task into step-by-step subtask. But this reasonable thinking step is what our current robots are lacking, because they don't have such an intelligent brain that we humans have. So what robots need is that the robots need an intelligent brain for both the language understanding and the general task planning if we want to apply the robots into our daily life. So, but unfortunately, current methods are not capable of this requirement. I mean, the current methods cannot form a very intelligent brain for it. For example, the current methods, they can do they can spin in the pan or they can arrange in the boxes, but they will fail to handle the long horizon tasks. Like to clean the spilled cook, you need first find a cleaning tool and then pick up the tool and move to a table and then undo what. So it's kind of like you divide. To fulfill this task, you need to first have this kind of reasoning ability to divide this task into a sequence of the actions, and then for each action you can use another module to handle it. But that's the main bottleneck we have right now. So the next question is, to get this kind of like the intelligent brain, what is which current technique most closely resembles this intelligent brain? So as you can imagine, or as you can guess, since the topic I would like to discuss tonight is combining the LLM or ChatGPT with the robots. So the answer is large language models or LLMs. But the reason is why. So we know large language models currently it has different kinds of the large models, and ChatGPT is the most famous one. So in this talk tonight, I will when I say the LLMs or when I say the large models, I will always refer it as ChatGPT. So we know ChatGPT is very capable, and it has been used by many different people, and every day I think. At least for me, I use it every day. So it is very easy to use it. In this interface, you just input your text questions, and then it will output a very good answers. And sometimes it will be wrong, but most of the time it is accurate. It's always correct. And the reason why this model is very powerful because it has a very huge amount of the parameters, numbers. For example, in this figure, the y-axis is different types of the large models, and the x-axis is a different type of large model, and the y-axis is the number of parameters in each model. And we will find that currently we have many companies are building a larger and larger model. And what the larger model is actually a model that over 10 billion characters, and they are trained on millions of text data sets to simulate the way humans speak. And since these large models are building to simulate the way humans speak, so they inherently have this kind of human's knowledge, or they inherently have this kind of common sense, because their token distribution is trying to simulate the human's speaking distribution. So since they have this kind of world knowledge or the common sense, then they are very strong in different tasks. In this figure, the y-axis is the x-axis is different kinds of tasks that ChatGPT can do, and then the y-axis is percentage of humans defeated. So if it's 100%, then I mean every human will be defeated by a large model. And then we can find that in this figure, the green bars are the strongest models that we can get, and we find in many different tasks it can beat most of the humans. So that's very powerful. Sometimes you will feel useful because in these different tasks, like the GRE or like the SAT, it performs very well. Yeah. So since large model is a very powerful tool, so our next question is whether it can be used to be a central brand for humans, for robots. For example, here for the same task, as I mentioned, the human will input the text instruction like, I spilled my Coke, can you bring me something to clean it up? And then the large model will output the answers. And this answer is like this kind of step-by-step planning. Find the sponge first, and then pick up the sponge, and then go to the table and do the next steps. So we can find that large models, if you give it the proper questions, the answers are already this kind of like the form that we want to guide the robots. It can work as an intelligent brain. So that's our hope, that we hope the large model thinks it has the common sense. Then while this common sense can be used to do the subtask plan. As a summary of our part one, there are two main points. The first main point is that the current robots still lack the intelligent brains for daily applications, and that's one of the bottlenecks hinder this broad application in our daily life. And another main point is that large models have human-like responses, and may be one possible solution. So you can see below is a general framework we propose right now, like a human can input the task, and then the large model can output this kind of step-by-step actions, and these step-by-step actions can later be used by the robots to do the planning. Yeah. So any question about the first part?
Great, thank you so much. So as a reminder, if you're joining us on the YouTube feed, please feel free to drop any questions that you have into the chat, and we can relay them to our speaker.
Yeah, so I guess are large language models only really getting better because we're giving them more data to start with, or are they also improving like under the hood, or is it just simply like we're brute forcing making them better by giving them a lot of stuff? Like you showed that slide, and it's like you need a lot to get good, but is it just because we're giving them a lot that they're good?
Yeah, good question. Actually, for the large models right now, it depends on both the model size and the number of data you used, and both are positively proportional to the performance of large models. And so right now the the current research, the conclusion is that if you use more good data, I mean the training data should also be good. Otherwise, it will be the garbage in, garbage out. Yeah. So yeah, and then more data you use, more powerful. Yeah, that's a common way. So that's why nowadays many big tech companies are spending money to recruit the users. On this task.
I was wondering, in your opinion, how much, or like what effect, or whether it's really the brain that we're lacking to have these like generalized task robots, or whether mechanisms and like actuators are part of that too. Like we're trying to find a tool on the robot, like actually physically build a robot that can do all these general tasks. Is that a barrier that we're also facing, or are we just missing the brain?
I think we are just missing a brain, and the reason we want the language model to do this task is because the language model nowadays have this kind of a similar brain-like behavior, or at least even if we don't call it as a brain, but some of its behavior is very similar to a brain. Yeah.
And then we had a question from the audience. It says, is embodied knowledge required for planning?
Oh yeah, that's a very good question, and actually this question will lead to my second part. In the second part, I will discuss about whether the embodied knowledge is needed for the language model to do the robotics tasks. Yeah.
If we have no further questions, then we can get started on the second part. Again, feel free to drop questions in the chat at any point.
Okay, so next I would like to answer the question: what if the plan generated by a language model is not practical? For example, a very common thing is that language model is not directly connected to the real world. So in this way, it does not know the situations in the real world. So many times the generated plan is not doable. For example, in our former example, one of the subtasks is to find the sponge. But actually, in many house or in many rooms, there is no sponge in the house. So even if the plan seems reasonable, but this plan will still fail in some situations. Yeah. So that's the reason why, as one audience just mentioned, we need to consider the embodied knowledge together with the LLM to guide the robots. So that leads to our second part about connecting the ChatGPT with the real world. So in this figure, it just did what we have mentioned. So in this figure, they are considering the two capabilities or two criteria for the larger model-based planning. So first is the correctness. I mean, the correctness is just measures whether you generated a plan is readable or it makes sense to the humans, so that the humans, as the judges, they will see whether this plan can lead to a success task execution. And the executability is what we are trying to emphasize right now. So executability means whether your generated plan is doable in the current environment. And we have found that they test on different kinds of the models, but even for the strongest model like the GPT-3, the executability is still like the 80%. So that means there is still like the 20% of the actions it proposed is not doable in the environment. That will lead to the failure. But actually, for our humans are in the right corner. Our humans are always proposing the actions that are doable right now. But we are not making sure it is correct. So humans, for example, it has executability like the 100%, but the correctness is like 80%. So our conclusion is that large models sometimes require unreliable actions since they are not connected to the real world. Then, how to solve this problem, or how to mitigate this gap? One very intuitive idea is, why not we just add an extra module to track the executability? I mean, we first use a larger model to propose the task plans, and then for each action it proposes, we just use another module to check whether it's doable or not right now. So this is the main idea that proposed in the one paper last year. And in that paper, the main idea is very intuitive and simple, but it's novel. So here, in our previous framework, that the human just say the task, like I spell my code, and then the LLM will output the candidate actions. I mean, it will output the possible actions that can do to handle this task, like find a sponge or go to the table, these kind of tasks. And what we are doing right now is that we are not only asking the LLM to give us the action that has the highest confidence by the model itself, we ask it to output all the candidate actions, and then also their confidence score. I mean, this confidence score measures whether LLM prefers which action. Yeah. Then after we get this LLM score, we build up another module. This module is called the executability estimation model, and it's another machine learning model. And this model is purely different from the LLM. And for this model, our input is each proposed action by the LLM, and then another input is the current state. I mean, the current state is the current state of the robots, the robots' velocity of the position of the drones, and the reapers, this kind of state. And then the environment image. I mean, this environment image will try to give the information like what the surroundings are like, and whether these surroundings can lead to a success action. And then you input these two together to the executability model, estimation model, and then this model outputs the action executability score. And I mean, this score they range from 0 to 1, and the most score means the model believes it's more doable for this action. For example, in this figure, you will see that the find a sponge is like the 0.6 score. So this means find a sponge compared to other actions is more doable right now. So then we can find that we get both the LLM score that measures the LLM's confidence, and also the executability score to measure whether this action is doable. Now the next step is to combine these two scores together. To combine these two scores, they are doing a very simple multiplication. I mean, these two scores, find a sponge, the LLM score and the action score, find a sponge, they are multiplied together. That will lead to a combined score. For example, the find a sponge is like the 0.3. So once we get the combined score, then we can among these candidate actions, we just choose the one action that with the highest score. Then in this figure, we can see that find a sponge is the most promising action. Then in this step, we choose the find a sponge. So for the LLM score, it's very simple to get because we just for example in the ChatGPT, we directly input the request, like for the current step, please output the candidate actions and append your confidence score to each action. And then the LLM will output not only the candidate score but also their confidence, not only the candidate actions but also their confidence score. That's very easy to get. And another thing is how to get the executability score. And in that work is estimated by the reinforcement learning. I mean, reinforcement learning is another machine learning neural network that is used to estimate the executability score here in that work. to get more information about what the reinforcement learning is, you can refer to this related material. I mean the course taught by the UC Berkeley. You can just search it in the YouTube. And so in their model, the input is first is environment image, and then the robot states like the position of joints and velocities and locations, and then is the action like find a sponge. And so they combine these three input together to the neural network, and then the neural network will output the executability score. So this model is trained on both the simulation data and the real data, and then this model will be fixed, and then to integrate with the LLM together to accomplish the whole framework. So then we can get this kind of a step-by-step plan. For example, here the same task, human will ask the question, and then in the first step, the LLM will output these 5 candidate actions. And in these 5 candidate actions, this blue is the LLM score, and the red is the executability score, and then the green is the combined score. And then you choose the one with the highest score, that is the find sponge. And then you do the action, you execute this action, find sponge. And then the robot will go to the next step, and it will observe the new environment. So the next action is pick up sponge, and then to the next state, and choose the third action is bring it to you. So this kind of step-by-step will finally lead a success task execution. So here is a video just illustrated this process. So here the user inputs the text, and then the robot will do this kind of planning. Yeah, it will first pick up the Coke can and then bring it into the trash can. And then for just find the sponge and bring it to the user. Yeah, so that's all of this framework. Then in this work, they also tested on different kinds of instructions, because in our common life, in our human life, we have different kinds of tasks, and we also have different kinds of expressions for the natural language. For example, the task can be very simple, like it can be just a natural language nouns, like bring me a fruit, or it can be a natural language verbs. This kind of task in each sentence, it's just include one action. Then that's very simple. But for some tasks, it will be very complex, like a long-run task. I spill my coke. Then in this way, this task is composed of many different actions together. So they test their method on different kinds of task expressions. And then here the blue is the framework that with the execution model, and the red is a framework without the execution model. And then you will find that the blue bar here is always higher than the red bar. That means after adding the execution model, the LLM works better to achieve a higher success rate. Yeah, so that's our conclusion. Adding executability estimation is important. So the summary of this second part is that to consider the real-world constraints, we can add an extra model to wipe out the unavailable actions. So that also answers the question proposed by the audience that how to consider the embodied knowledge when integrating the larger models into the robot planning. We can add an extra model to track the embodied availability. Yeah. So, any questions on this part 2?
Great. Thank you so much again. As another reminder, if you join us on the YouTube feed, please feel free to drop your questions in the chat.
So, do you have to like keep? So I assume that the robot in that video was like already had instructions for how to like move and grab and that kind of thing. But I could imagine that you want robots that can change a little bit of what they're doing in response to user queries. So would you have to then add on like another language model that's like coding for the robot to get it to do what you want to do? Like I know that you can use like ChatGPT to write, you know, programming bits and code, and sometimes it works, sometimes it doesn't. But like, would you have to then consider, if you're trying to make this even more generalizable, like another model of the visual model, the understanding model, and then like the execution model? Like actually, can we make the robot do this physically?
Yes, very good question. The answer is yes, and that's what many researchers are currently doing right now. I mean, they can use different LLM agents, and then each agent will take charge of one component. Like one large model is built to understand the environment, and another is to just adjust the actions. I mean, the parameters in the action models, and then another is for task planning.
Great. A question that we have in the chat. Is the model trained to get action executability score, or could you use a pre-trained vision language model?
Yeah, this is a very good question, and I think this question is proposed by the expert in this domain, like whether this model should be specialized in these specific tasks you design, or you can use another very general model so that you can skip this training process. For this work I mentioned, proposed by last year, they used a specialized model to do these kind of motion things or action things. So that's why they collect a huge amount of data for both the simulation and experiments to train their model. And as for whether the current vision language model can be used to this task, I think that's a good question, because we know the current model, like the GPT-4, it has a vision version. I mean, you can not only input the text, you can also input the image to ask it to understand whether it can do or not. And based on my personal experiments, is that sometimes it works. I mean, for some simple tasks it works, but sometimes it will fail because the current vision language model is still poorly in some tasks. Like for example, in the whole image, you will ask it how many boxes it has. Then some is good, some is not correct. So that's why I think for the simple tasks you can use the vision language model, but so for complex tasks, it's better that you can build up the model to fine tune it.
Great. And then I was also wondering, do you know why the Coke can didn't make it in the trash can? And did they consider that a failure, or was it a success because it tried to do the right thing?
Oh yeah. So why it knows that the Coke can should be filled to the trash can? That comes from the common sense. I mean, the common knowledge, like the LLM knows you need to put the Coke can into the trash bin. But for example, sometimes it will the execution will fail. For example, if the trash can is full, and then the trash bin is full, and then the Coke can cannot be dropped into the trash bin. That's why, as another audience mentioned, we need another LLM to check the state, to check whether this your action is successful or not. Yeah.
So with the kind of, as you're saying this now, I'm realizing like you're going to need a lot of either models that are pre-trained or a lot of new models to do one thing. there like a sense of how feasible it is to have all of those on like one physical location, I guess? Like as they start adding up, they take way more like memory or RAM or operating power to keep doing each thing consistently. Like even in the video, the robot would like pause for a bit, where I assume it was calculating what to do. Is it like going to get exponentially slower each one that you have?
Okay, that's a very good question. That's also something that I want to mention in the part 3. I mean, currently the language model is very big, and for these big models, you need to the hardware requirements to hold these models are very high. You need many GPUs to hold it, and that's not doable for one robot because the price will be higher and higher. So one way people are doing it right now is to try to compress the model size, but make its capability as to be satisfying enough. Yeah. That's one thing I want to I will expand further in the part 3.
All right. One other question in the chat. Also, can you use visual response from the action to replan?
Great question. The answer is yes. Yeah, and that's a very great question. Currently there are some works that you use a vision to check whether the action is successful or not. For example, you can use a vision model to check whether your gripper is grab something or not. Then these kind of actions can be converted into the text description, and then it can be put into the LLM again to let it know, okay, what's the current state for the robots.
Great, thanks so much for your questions. We can move on to part 3.
Okay, so then, as many audience are right now discussing, so our next question is, can LLM be an QRO planner for robots? If it's true, then the situation is very good. So if it's true, then I think another kind of like evolution in our common life will come. But the answer is, unfortunately, it's not. Sometimes using LLM as a device planner will fail, and this kind of failure comes from different reasons. And so in the part 3, I would like to discuss some of the challenges that we are still facing, and for each kind of challenge, what are the possible solutions we can do. And for each challenge, I will also discuss one work from our group. That's one possible solution that we are proposing. That leads to our part 3, the future prospects in ChatGPT robotics. So the fatal case 1 is that actually, so if you can see in our previous discussion, the LLM is responsible for the planning of the task sequences. I mean, it's kind of like the task planning. I mean, here the task planning, the definition is that it plans the subtask sequence, like the places to visit or the object to grasp, this kind of subtask sequences. But actually, a very big problem is that the motion planning part is missing here. So the motion planning part here, the definition is that motion planning, you should try to plan the trajectory of the robot or the robot arms, like the trajectory of the cars in the autonomous driving, or the trajectory of the grasping. For the grasping, like how the robot arm going to grasp, pick the robot, pick the Coke can, but it should not climb onto other objects. That's a very challenging problem. But the main bottleneck here is that in the previous from we mentioned, the large model is disconnected from the motion planning part. Yeah, but actually, if you think about this problem, there are some tasks that require the task planning and motion planning together. For example, in this very typical problem is the showcase path task. I mean, you just ask the robots to visit all the buildings with the showcase path. Then in this way, the big problem is that the task sequence is generally the order of the buildings to visit. But it highly depends, since you also need to get the showcase path. So this kind of the sequence of places you need to visit, it highly depends on the distance to the building and this distance will change dynamically because your robot is moving. So in this problem, the task planning and motion planning, they are dependent on each other. Yeah, I mean the building sequence you need to build, it highly depends on the trajectory optimization. But also trajectory optimization also depends on your building sequence. So, but the challenging thing is that language models, they are not good at understanding the space and the optimization because it is a pure text-based model. So this kind of spatial understanding and this kind of numerical optimization is poor for the current LLMs right now. So one possible solution we propose here is that we can integrate the LLMs with the traditional planners. I mean, there are already many traditional planners in the robotics domain that they are specialized in this kind of like the task motion and motion planning, but these tools, they are designed for one specific task, not the general tasks. So what we want the language model to do here is to, like, the language model get the input of the human's instructions, and then it will understand, okay, so this problem belongs to which task, and then it just use the tools in this specific problem. So in this way, the LLM is just going to do this kind of like translation and tracking. For example, in our framework, the input is still the language instruction from the humans, and then we also input the state observation. And the state observation is contain what kind of the objects in this environment the robot is located, and then we put to the language model. And what's the task that LLM is going to do is to do the translation things. So we ask the LLM to translate this kind of language instruction into the formal task specification. And this formal task specification is an intermediate representation that can be further used by the traditional planner to output a final plan. For example, here we get this formal task specification, and then we put it into the algorithm-based syntactic checker and LLM iteration. Then this means because your formal task specification should be syntactically correct, it should be syntactically understandable by your traditional planners. So we need another algorithm-based method to check whether it's syntactically correct. If it's not, then you need to feedback to the LLM again to correct it. Then you put it into the formal planner to output the trajectory. So once you get the trajectory, you can convert this trajectory into the state sequence. Like in the current time 0, you are in the pigeon, and in the 10 seconds later, you are in the bedroom. It's kind of a state sequence, and this state sequence will go back to the LLM again to check whether your current output plan is consistent with your initial language instruction. So then the LLM we are going to feedback if the LLM thinks the current plan is consistent with the natural language instruction, then it's converted. So you just output the final trajectory. If not, we require the language model to output to provide the intermediate representation, and then to output the formal planner again. So in our framework, we are not asking the LLM to be a direct planner. We ask it to be a translator and a checker. So in this way, we can because the LLM is good at the language understanding, and the algorithm-based method is the traditional planner is good at this kind of the task and motion planning or the numerical optimization. So we can combine the advantages of the both tools together. So here is one example of our work. So here in this environment, the three cars should visit all the three goals, but then visit and then move back to to the transportation, and then move back to the pink area. So, but the challenging thing here is that this task should be completed in the limited time. So, and also these robots, they should avoid the black walls, and also they should avoid the collision with each other. Then you need to do this kind of the task and motion planning together. Another task is that the 4 zooms are targeted to pass through this small hole, but they should not collide with each other, also they should not collide onto the wall. So, so this is another example of the task and motion planning using our framework. Another failure case is the multi-robot collaboration. So, as we introduced in the part 2, their framework is just for the single robot action, for a single robot task planning. But in most cases, to improve the efficiency, there should be many different robots in the whole field, and you are trying to arrange these robots so that these robots, they can communicate with each other and arrange their tasks to make the whole arrangement more efficient. And but then a big problem is if you use the LLM for the task assignment, then how do this group of the robots they communicate with each other? I mean, in which way they are communicating with each other? So, but if we think about this problem, we can come up with 2 very intuitive communication from like our humans. The first framework is that each robot is assigned with one LLM to discuss the plan with equal power. I mean, these robots they are assigned with one LLM, and then these LLMs they are discussing with each other to assign the tasks, and then they are doing this kind of long dialogues. And once this dialogue is stopped, and then this group of the LLM agents will say, okay, we can get the final plan. That's one very intuitive dialogue framework. It's very similar to our humans group discussion. It's kind of long dialogue. But we find the problem is that if you really do this kind of implementation for the LLMs, you'll find the dialogue cannot be concluded timely. I mean, there are many cases that these LLMs will discuss with each other, and then after the 10 minutes, it's still not finishing. But you just find that you spend a lot of money, but then the dialogue, then this group of the LLM agents they still does not feedback the final plan to you. And another intuitive framework is a centralized one. I mean, there is just one central LLM that it plans all the subtasks for all the robots together. And that's why very efficient. I mean, there is no dialogue between the LLM agents. And these LLMs, they are, and there is one LLM that will handle all the things. But we found one problem is that the central planner can make simple mistakes. Because the LLM sometimes will make other mistakes. And then if there is one plan for just one robot that will fail, then the whole group of the robots they are very risky because they may collide with each other, or their whole task will come into the failure. So our modification to this framework is that we can first, for the round dialogue framework, we can introduce another extra LLM to first send the initial plan to each LLM, and then based on this initial plan, the other LLMs for each robot they carry out the round discussion. That will save some of the discussion time, because in this way you are trying to put up the suboptimal plan by an extra LLM, and then other LLMs they are discussing with each other to make the optimization easier. Yeah, but what I find is that though it has some efficiency, but it's not such satisfying. I mean, still in many cases, this dialog will not end template. And also one very bad thing is that this long discussion will make your text to be very longer and longer. So the important information will be forgotten in this kind of long discussion. And another framework is to modify the centralized framework. So here, still the central LLM will give the actions to each robot, action plans to each robot, and then each robot is implemented with one LLM to send the feedback to the central LLM. Now in this way, the local LLMs will going to check whether the central plan has some mistakes or whether it's perfect. If it has mistakes, then the feedback will be directly passed to the central LLM to correct it. And we found that this framework, among all the 4 frameworks we discussed, is more efficient. It's both efficient and effective. I mean, the task success rate is high. So here is one video that we want to show for this kind of discussion framework. So here are the 3 robot arms. They are working together to move all the boxes into the same colored box. And but each robot arm, they are constrained on their arm span. So they should work together to move the robot to their target box. So in this way, they should discuss with each other. And also, they should consider like some dynamical problems. For example, sometimes the boxes will slip out of the grippers. Then they should do the replan again. So then they should carry out this kind of long discussion to make the final plan. So that's all about the standard possible failure and its possible solution. For the failure case 3, as just one audience mentioned, the inference cost of LLMs is too high. So by saying the inference cost, I mean this inference cost can be from many parts. First is the computational time. I mean, you need to use these kind of models, language models, and this language model first is very big. Another thing is that you may still need to connect many models together. That will make your time latency to be very high. But in our real application of robots, we want it to have the timely feedback. So in this way, you need to think about how to decrease the computational time. And another thing is the GPU usage. I mean, the larger the model is, then the more GPU it will be required. But we all know that nowadays the GPU is the price is very high, so that will cost too much money. And another thing is the energy consumption. I mean, for the LLMs, to hold this kind of very large models, we need to use many GPUs, and each GPU will consume much energy. Because it runs all the time. And it runs in many days. So in this way, the energy consumption will be another concern. So based on this, one possible target is that we will help to reducing the model size but still maintaining its capability. So to reduce the model size but maintaining its capability, that will be a very challenging problem. Because we know in my previous discussion, the model is positively, its performance is positively correlated with the model size. But what we are hoping to do here is that our intuition is like this. For the GPT-4, for the large model, like the largest model right now, it has 1T parameters, and it is very good at different kinds of tasks, like the generation or modality or multimodality or planning or coding or math or this kind of different tasks is very good. So it's very strong. But for the models, for very small models, like not larger models, in all different dimensions of the tasks, it's not very good. It's very weak. So what we are trying to do right now here is that whether we can have this kind of model that is good at one specific task, one specific capability, but for other capabilities is poor. But that's fine because we can just use this model for this specific task. So that's our intuition. So what we are doing here is that we are trying to fine-tune this small model to be a stronger, relatively stronger model. That it is stronger in some parts, but it is stronger in the planning capability. But for other capabilities, it's not such it's not such powerful. But that's still satisfying. Yeah, for us. Yeah. So that's our that's our whole idea here. Now one bottleneck here is that first, how to fine-tune this small model, how to build up data sets to strengthen the planning capability of small models. I mean, where the data come from? Because the data set is very important. So that's then I will introduce another part is the knowledge distillation from large models. Because the main idea is also very simple. Because the large models right now, they are very good at nearly all these kind of capabilities. Then why don't we can ask the small model to simulate the answers of the large models? Then in this way, you are trying to the large model is a teacher and the small model is a student. And because right now you don't have this kind of data set, so you just input different kind of questions to the large model, and then the large model will give you different answers. And then for these answers, you can regard them as true answers or as the correct answers. So you ask the small models to simulate this. So yeah, that's a very intuitive but very useful idea. So the framework is like this. You first use the algorithm to synthesize, or you can just collect from humans for different kinds of questions or different kinds of task instructions. And then you input to the large model like the GPT-3 or GPT-4. And these large models will give you the output. You can directly give you the plan, or as I mentioned before, like in our framework, you can output the task representation. Then, after you getting these answers from the large models, first you still need to check whether this output is syntactic correct. But that can be checked by the rule-based manner. Another thing is that for many answers, even if it is syntactic correct, it will sometimes semantically it will still not be very good. Then in theory, that's why you need a human in the loop you need to have the humans to correct the answers. Then after the humans or after the experts correction, you will get the final plan or final task representation. So after you get the task representation, then you just get these kind of pairs. I mean, these kind of pairs, first the input natural language instruction, and then the output is the final plan or the final task representation. That's your creative data set. And the role that the larger model here, the GPT-3 or GPT-4 here are doing is to give an ad hoc answer. And then the human's responsibility is just to correct these answers. So that will make a human's burden to create the data set to be less and less. So then after we get this created data set, we can try to fine-tune the smaller model based on it. So here in our framework, what we are doing is to try to compress the larger model to a very small model on the translation task in the former framework I mentioned. So here we use the GPT-3 as the bottleneck, and then we try to compress it into a very small model T5, and the compression ratio is like 200 times, and we created a data set with 25K natural language and the representation pairs to do it. So that's our performance. We'll find that actually the small model fine-tuned on the created data set will perform very good on these 3 different domains. And it's even better than the GPT-3 method because we have a human in the loop. So humans can correct the errors made by the larger model. And then the smaller model will perform even much better than the larger model after being fine-tuned on this specific task. I mean, for this specific task, it's better. But for other tasks, it's not as good as the large models. But that's fine because in the framework we don't use other capabilities. So that's our demo website. This demo website, if you scan the QR code or if you direct visit the website, you'll get this kind of like a translation web page, and then in this web page you input your natural language instruction, and then you click on translation. The output will be the translated representation. So that's our work to compress a larger model to a smaller one. But our task here is to do the translation task, as I mentioned in the Wolfram. But another recent work done by other group, other researchers, they are trying to. The idea is very similar to us, but they are trying to develop trying to fine-tune a smaller model to handle the task planning task. I mean, here the large model is the smaller fine-tuned model is directly output the execution plan, and what we are trying to do here is to build out a data set. The task is about like the operating systems database or web navigation, this kind of data tasks, and then they fine-tune it, and then they find the performance is much better. So this general idea, like you constructed a data set with the assistance of the larger models, and also you still need the human in the loop, a human expert to correct it, and then you use this data set to fine-tune the smaller model, and then to make the model both much smaller in the size and also even more powerful than a large model. That's a very general idea. Recently, more and more popular. So the summary of the part 3 is that the first part is that we can combine the large model planner with the traditional algorithm-based planner in more complex tasks. I mean, these complex tasks can be the tasks that involve the task and motion planning together, and involve many numerical optimization and reasoning things. Another thing is that the discussion from our LLMs can be further optimized to apply into multi-robot situations. The third thing is that we can distill smaller model may be the general trend in the future. Yeah. So finally, let us return back into the initial question that I answered, like how far are we from these conditions? How far are we from these kind of general robots that can do the common different tasks for us in both the home, in both the room, and in both the office? That's still a question I can't answer right now, but I'm sure that the appearance of the LLMs will try to make this gap smaller. So that's the whole of our discussion today. And thank you, the SITM, for this activity, and thanks for the support of the Harvard. Yeah, that's all. Thank you.
Great, thank you for a fantastic talk. As a final reminder, or if you're just joining us now, please feel free to type any questions that you have into the chat.
So how small can you make the student models that you're training on? Like you said, it was like from like 1T eventually to like 10 billion, but could you go even smaller? It looked like they were doing really, really, really well, even better than the teacher model when there's human correction. So could you make them even smaller and smaller? Is there like a limit to how small they can get?
Oh yeah, that's a great question. Actually, so right now, how small for the model depends on the requirement from the task and the requirement of your hardware. I mean, right now many groups they are trying to do the smaller model on the 7 billion model. Why is 7 billion? Because 7 billion is suitable for just one GPU to host it, and one GPU is affordable for many hardware tasks. Like it's even affordable for many computers, you self laptops, and also one GPU is affordable for the robots. So that's why right now most people are doing 7 billion, because there is always a trade-off between the requirements of the data set and the model size. So the smaller model will cost more data set, and if you are just finding an intermediate one that the model size is small enough, and also it requires this kind of amount of the data that still affordable, that's okay.
And one question we have in the chat, is planning a general capability, i.e. could training on tasks require reasoning, visual question answering, help robotics planning? Could training on tasks require reasoning, visual question answering, help?
So I think I need the ChatGPT to summarize this question.
All right. Yeah, maybe is planning a general capability, does that?
I see. So I think the planning is kind of a capability that you are planning for both the task and motion, and yeah, it is a general capability. I mean, there are many different situations that require the planning capability, but if you can confine your application situation into, for example, into just in the room or in the software development, then this kind of planning capability are just require several tasks, several planning capabilities, not general all the capabilities. That's why you can use a smaller model.
And I was wondering, so what kind of advances would we need to remove the human from that loop in training this model?
Great question. Currently, we don't have a better solution. That we still need humans, because humans is the most advanced intelligence. At least we don't find aliens. Yeah. So humans should be the most advanced intelligence. So we still need humans. But as the larger model's performance is higher and higher, then humans' burden will be less and less. So yeah, that's a general trend.
And then one question that I always like to ask, just sort of choose your own adventure question, either what brought you to this field, or like what really excites you about this field?
Great question. So I think one answer is that I find this field is very interesting. I mean, this field compared to other fields, this field is developing very rapidly. I mean, in every month, in every week, in every day, there are many new things come up, and but you still are on a very high pressure because you need to learn many stuff in each day. But that's very interesting because your brain will be new and new because you are accepting the new information in each day.
Great. If we have no further questions, then I'd like to say thank you to everyone who joined us, and thank you to our speaker once again.
And we will have another talk next week at the same time, November 8th, 7 p.m., both live streamed on our YouTube and also in Northwest Building B103. So we hope to see you then.